Yeah, let's do 8.28. We got the asteroids colliding. We got this bad boy coming in here at 40 meters per second. He runs into this guy B, who apparently is just sitting there minding his own business. Okay, A goes up like this at 30 degrees. B goes down like that at 45 degrees. They have the same mass. We're going to find the speed of each one. So to do that, there's no internal forces. We can conserve momentum. Okay, but because there's an x and a y force, we're going to have to conserve, momentum in both the x and the y direction. Now, initially, if we look at v sub x, I'm going to look at just conserving the sum of the x momentum first. Okay. Well, A has a momentum to start with. It has m, whatever that is, okay, times 40 meters per second. Okay. And that's going to equal m times whatever the VA is, I don't know what that is, times the cosine of 30 degrees plus the mass of the other, remember they're all the same masses, times VB, I don't know what that is either, times the cosine of 45 degrees. Okay, there we go. All right, notice all the m's divide out, so we're going to actually cancel all those, and I'm going to sub in what the numbers are. The cosine of 30, let me close it up slightly better if I can. Okay, cosine of 30 is going to be root 3 over 2, or 0.866. The cosine of 45 is going to be root 2 over 2, or 0.707. So I'm going to have, and all these masses are going to divide away. So I'm going to have 40 equals VA times 0.866, better, plus, I'm going to put this in the front this time, 0.707 VB. All right, so that's for my x momentum, but my y momentum is going to look different than that. Okay, because I don't have any initial y momentum. The asteroid is only moving horizontally when it strikes the second one. So what that means is that whatever the y momentum is of A is going to be equal to the y momentum of B, which means that m times VA times the sine of 30 is going to equal mVB times the sine of 45 degrees. Okay. And it actually turns out to be okay for us. The masses divide out, and we get that 0.5 VA equals 0.707 VB. Well, we've got two equations and two unknowns. Those are pretty solvable by substitution. So we can just go ahead and replace those. We can do point 5. We can say that VA equals 0.707 VB divided by 0.5, or 1.41. 4, I guess, VB, and then substitute that in over here. So then we'll have, we'll draw a little box around these, and then we'll say 40 equals 0.866 times 1.414 VB plus 0.707 VB. Okay. If we multiply those out, we get 1.22 VB plus 0.707 VB 40 equals all that. Okay, so then we get 40 equals 1.93 VB. We divide, we get that VB equals 20.7 meters per second. Okay. That turns out pretty good. And then we can substitute this number here over here. And we can solve for VA. When we do that, VA ends up being like 29.3 meters per second. Part B asks us to find the fraction of the original kinetic energy at asteroid A that dissipates during the collision. Well, we can find the fraction of the original energy that asteroid A dissipates during the collision. Then we'll just take 1 minus all that. So let's find the fraction first. The fraction would be the kinetic energy at A plus the kinetic energy at B. These are both after. Divided by the kinetic energy at A before. I didn't include B because B didn't have any kinetic energy before. So it's going to be 1/2 times mass times, remember we figured out that that velocity was, for A was 29.3 squared plus 1/2 times m times 20.7 squared, all divided by 1/2 times m times 40. Remember that was the original velocity squared. Well, you can see that every term has a half in it, so we can make all those go away. And every term also has the m in it, so we can make all those go away. So we're really, to find the percentage, all we're really doing is taking 29.3 squared plus 20.7 squared and dividing the sum of those by 40 squared. When we do that, we get 0.804. So that means that 80.4% of the original energy is left in the collision after. So if we want to find out the amount left, the percentage dissipated, we just set that equal to 1 minus that. And that's going to be 0.196 maybe, which is equal to 19.6%. So a little under 20% of the energy still remains when you're after, it's dissipated, sorry. A little over 80% remains. A little less than 20% gets dissipated. Could be through sound or heat or light. We don't know. We just know that we don't get to have it when we're done with the collision.